In this module, we learn about the two logic families CMOS and ECL. CMOS refer to Complementary Metal Oxide Semiconductor Logic Family and ECL corresponds to Emitter coupled logic family. Let us first start with CMOS. Basic component that is fabricated is MOSFET. We know that there are two types of MOSFETs, P-type and N-type. This CMOS logic family is very popular because of the high density of fabrication and low power dissipation. We can fabricate P-type as well as N-type MOSFETs on the same chip, and hence it is called as Complementary Semiconductor Metal Oxide Semiconductor Logic Family. Different logic circuits can be fabricated by combining these two types of MOSFETs. Enhancement mode and depletion mode are other classifications corresponding to the CMOS. This particular logic family is very popular because of these advantages. After considering different aspects of CMOS logic family, let us begin with the next logic family, that is ECL. It is emitter coupled logic family. It is bipolar non-saturating logic family. It is something different than whatever we have studied earlier in TTL or CMOS. In case of TTL, we consider the transistors are either in cutoff or in saturation. So there is a problem of storage time and you cannot achieve the propagation delay or the speed below certain value. But in case of ECL, we can achieve high speed because the transistors are never in cutoff or in saturation, they are operated on a linear region, and hence it is called as non-saturating logic family. The levels, that is the logic levels, are also slightly different than that of the TTL or CMOS. Generally in TTL we say logic 0 as 0 volt and logic 1 as plus 5 volt. But in case of ECL, these logic levels are slightly different. We will see them as we proceed in the module. These logic families are fastest logic family amongst all the logic families which we have discussed, and hence this is popular. Learning objectives for CMOS logic family. In this particular module, we first see how this CMOS logic family is important. So, let us understand what is MOS technology. Then learn about PMOS and NMOS technology. Understand the basics of CMOS technology. Learn about output configurations of CMOS. Understand classification of CMOS family. Compare the subfamilies on the basis of performance parameters, and also understand how to interface CMOS gates. Learning objectives ECL. We first need to understand what is non-saturating logic in ECL family. We need to understand the features of ECL family. Understand the working of basic logic gates in ECL family. Know about different subfamilies of this. Compare them on the basis of performance parameters. And at the end, we see how to interface ECL and TTL logic families. Let us begin with CMOS, that is Complementary Metal Oxide Semiconductor Logic Family. MOSFET Basics. MOSFETs are classified as enhancement mode and depletion mode. As we know that a field effect transistor is made by growing a very thin layer of SiO2 of the order of 0.1 micrometer thickness over a semiconductor material. A metal such as aluminum is deposited over the dielectric layer of SiO2. This structure is known as metal oxide semiconductor field effect transistor or MOSFET. The metal gate is insulated from the channel and therefore it is also called as insulated gate FET, that is IGFET. Similar to junction field effect transistors, we can have N channel as well as P channel MOSFETs. Since N channel devices are more popular than P channel devices, this is because of the higher speed. Basic principle of operations of P channel and N channel MOSFETs are same. P channel MOSFETs are considered as absolute for independent or individual devices, but are found to be used in complementary MOS, that is CMOS technology. MOSFET Basics. Two N-type regions known as source and the drain are diffused into a P-type substrate. A thin layer of silicon dioxide is grown over this, and by masking, etching and metallization processes, metallic contacts are taken from the source and the drain, and a metal gate is formed above the dielectric layer. In this device, no channel exists between the source and the drain unless a positive voltage greater than threshold voltage Vt is applied at the gate. Due to this, field from the gate, the electrons, that is minority charge carriers from the substrate, are attracted towards the gate between the source and the gate regions, and it will change this region between the source and the drain to N type, thereby forming a N channel. This channel makes it possible for the electrons to flow from the source to the drain when positive voltage is applied at the drain. Since the application of the positive voltage at the gate enhances the channel width, this device is referred to as enhancement mode device or enhancement MOSFET. An increase in the drain voltage increases the drain current, producing resistor type operation for small voltages similar to JFET. Pinch off occurs when the drain to source voltage is sufficiently large, which reduces the field near the drain to 0 and makes the drain current relatively constant. CMOS subfamilies. The CMOS logic family, like TTL, has number of subfamilies. The basic difference between different CMOS logic subfamilies lies in the fabrication process used and not in the design of the circuits. Let us know about the performance of these subfamilies in detail. Consider 4000 series. The 4000 series CMOS ICs introduced by RCA were the first to arrive on the scene from the CMOS logic family. The 4000A CMOS subfamily is absolute now and has been replaced by 4000B and 4000UB subfamilies. We will therefore not discuss it in detail. The 4000B series is in high voltage version of 4000A series, and also all the outputs of this series are buffered. The 4000UB series is also high voltage version of 4000A series, but here the outputs are not buffered. A buffered CMOS device is one that has constant output impedance irrespective of the logic status of the inputs. If we recall the internal schematic of basic CMOS logic gates, this variation in the output impedance occurs owing to the variations combinations of MOSFETs that conduct for a given input combination. All buffer devices are designated by suffix B and referred to as 4000 B series. The 4000 series devices that meet 4000 B series specification except for VIL and VIH specifications and that the outputs are not buffered are called as unbuffered devices and are said to belong to 4000 UB series. Variations in the output impedance of unbuffered gates is larger for gates with larger number of inputs. Characteristic features of some CMOS subfamilies are listed below. They are VIH buffered devices, VIH for unbuffered devices, IIH, IOH, IOL, VIL for buffered as well as for unbuffered devices, again VOH, VOL and VDD, and these parameters are listed for different values of VDD. Parameters such as propagation delay, noise margin are also listed here. Let us consider another CMOS subfamily, that is CMOS 7400 series. It is referred as 74C series. The 74C CMOS subfamily offers pin-to-pin replacement of the 74 series TTL logic functions. For instance, if we consider 7400 as a quad 2 input NAND in standard TTL, then 74C00 is quad 2 input NAND with the same pin connections as in CMOS. The characteristic parameters of 74C series CMOS are more or less the same as that of the 4000 series devices. The characteristic parameters of 74C, 74HC, 74HCT, 74AC and 74ACT series CMOS are summarized as follows. These parameters are calculated for VDD equal to 5 volt. The parameters are VIH minimum, VOH minimum, VIL maximum, VOL maximum, IIH maximum, IIL maximum, IOH maximum, VNH, VNL, power dissipation per gate, speed power product. BiCMOS logic family. In BiCMOS logic family, bipolar and CMOS devices are integrated on a single chip. The objective is to derive the advantages individually present in bipolar and CMOS logic families. The bipolar logic families such as TTL and ECL has the advantage of faster switching speed and larger output drive current capability, and CMOS logic has the advantage of low power dissipation, higher noise margin and larger packing density. BiCMOS logic attempts to get the best of both the logic families. There are two major categories of BiCMOS logic devices. In one type of device, moderate speed bipolar circuits are combined with high performance CMOS circuits. Here, CMOS circuitry continues to provide low power dissipation and larger packing density. Selective use of bipolar circuits gives improved performance. In the other category, the bipolar component is optimized to produce high performance circuitry. Comparison of different logic families. Table shows a comparison of various performance parameters of the three logic families, namely TTL, CMOS and ECL. The data given in case of CMOS families are for VDD equal to 5 volt. In case of ECL family, the data is for VEE equal to minus 5.2 volt. Interfacing different logic families. CMOS and TTL are the two most popular and widely used logic families. Although ICs of the same logic family have no special interface requirements, that means one can directly connect the output of one to the input of the other. The same is not true if we have to interconnect digital ICs belonging to different logic families. Incompatibility of ICs belonging to different families mainly arises from different voltage levels and current requirements associated with low and high logic states in the inputs and outputs. In this, we will discuss simple interface techniques that can be used for CMOS to TTL and TTL to CMOS, TTL to ECL and ECL to TTL, and CMOS to ECL and ECL to CMOS. Interfacing CMOS to TTL. We know that the TTL family has a recommended supply voltage of plus 5 volt, whereas the CMOS family devices can operate over a wide supply voltage range of 3 to 18 volt. So, both the ICs could operate from 5 volt. As far as the voltage levels in the two logic states are concerned, the two have become compatible. The CMOS output has a VOH minimum of 4.95 volt for VCC equal to 5 volt and VOL max of 0.05 volt, which is compatible with VIH min and VIL max requirements of approximately 2 and 0.8 volt respectively for TTL family devices. In CMOS to TTL interface, with the two devices operating on the same VCC, one can have voltage level compatibility, but current level compatibility must be considered. That is, in the low state, the output current sinking capability of CMOS IC in question must at least equal to the input current sinking requirement of the TTL IC being driven. Similarly, in the high state, the high output current drive capability of CMOS IC must equal or exceed the high level input current requirement of TTL IC. For a proper interface, both the above conditions must meet. As a rule of thumb, a CMOS IC belonging to 4000B family, which is most widely used CMOS family, can feed one LS-TTL or two low power TTL unit loads. When a CMOS IC needs to drive standard TTL or a Schottky TTL device, a CMOS buffer is used. 4049B and 4050B are hex buffers of inverters and non-inverting type respectively, with each buffer capable of driving two standard TTL loads. Figure below shows CMOS to TTL interface with both devices operating from plus 5 volt supply and the CMOS IC driving a low power TTL or a low power Schottky TTL device. TTL to CMOS interface. In the TTL to CMOS interface, current compatibility is always there. The voltage level compatibility in the two states is a problem. VOH min of TTL devices is too low as regards the VIH min requirement of CMOS devices. When the two devices are operating on the same power supply voltage, that is 5 volt, a pull-up resistance of 10 kilo ohm achieves compatibility as shown in the figure on the slide. The pull-up resistor causes the TTL outputs to rise to about 5 volt when high. When the two are operating on the different power supplies, one of the simplest interface technique is to use transistor as a switch in between the two. Another technique is to use open collector type TTL buffer interfacing TTL to ECL and ECL to TTL. TTL to ECL and ECL to TTL interface connections are not as simple owing to the widely different power supply requirements of the two types. ECL devices have differential inputs and the differential outputs. The special chips are available that can take care of all these aspects. These are known as level translators. MC10124 is one such quad TTL to ECL level translator. It consists of 4 independent single input and complementary output translator inside the chip. Figure shows a TTL to ECL interface using MC10124. MC10125 is a level translator for ECL to TTL interface. It has differential inputs and single ended output. Figure shows typical interface schematic using MC10125. Note that the interface schematic in the figure is only one of the available 4 translators that are used. CMOS to ECL and ECL to CMOS interface. CMOS to ECL and ECL to CMOS interface are similar to TTL to ECL and ECL to TTL interface. Again, dedicated level translators are available, that is MC10352 for instance is a quad CMOS to ECL level translator. A CMOS to ECL interface is also possible by firstly converting CMOS to TTL and then TTL to ECL, again by using MC10124 or a similar chip. Figure shows the arrangement for the same. Similarly, an ECL to CMOS interface is possible having an ECL to TTL interface using MC10125 or similar chip followed by a TTL to CMOS interface as shown in the figure. Some CMOS ICs of 4000 series. 4000 is dual 3 input NOR gate plus 1 inverter. So, the number of gates are 2 and the number of inputs are 3. 4001 is quad 2 input NOR gate, quad means 4 and 2 inputs. 4002 dual 4 input NOR gate, number of gates 2, number of inputs 4. 4007 dual complementary pair plus 1 inverter. So, number of gates are 2 because it is dual and number of inputs are 1. 4009 is hex inverting buffer. So, number of gates are 6 and number of inputs 1. 4010 hex non-inverting buffer, again number of gates are 6 and number of inputs are 1 for each gate. 4011 buffered quad 2 input NAND gate. So, number of gates are 4 because it is quad and there are 2 inputs for each gate. ECL, that is emitter coupled logic. It is a non-saturating logic. In order to understand what is non-saturating logic, consider a simple transistor which is used as an amplifier. So, if at the input you give sine wave, the output is amplified but out of phase. When you use transistor as an amplifier, it is operated in a linear region. If you look at the graph, then you can see that there are 2 regions which are nonlinear regions and one region called as linear region. So, nonlinear region is cutoff and saturation region and there is a linear region where there is a linear relationship between voltage, input voltage and the output voltage. When you consider TTL logic family, the output is logic 0 or logic 1 corresponds to transistor operated in cutoff region or in the saturation region. But in this, the propagation time is more. The propagation delay increases because we have considered the transistors as on or off to be either cut off or in saturation. But when they switch from one state to other state, that is from on to off, they does not go to these states quickly. This is due to charge stored in the base region. It is shown in the figure. You can see that there is a NPN type of transistor which is operated either in the cutoff region or in the saturated region. To switch it from one state to other state, the stored charge in the base region has to be nullified. So, there is some time which is required for this and which is related to the delay. This propagation delay time is reduced in ECL. In ECL, the linear region is considered and we can fix the logic 1 and logic 0 along this linear region. Since the transistor does not go to full cutoff or full saturation, the propagation delay is very less. Emitter coupled logic basic ECL circuit. The basic idea of current mode logic is given by inverter or buffer circuit shown on the slide. This circuit has both an inverting output out 1 and non-inverting output out 2. Two transistors are connected as a differential amplifier with a common emitter resistor. The supply voltages for this are VCC 5 volt, VBB 4 and VEE 0, and the input low and high levels are defined to be 3.6 and 4.4 volt. This circuit actually produces output low and high levels that are 0.6 volt higher, that is 4.2 and 5 volt, but this is corrected in real ECL circuits. When Vin is high as shown in the figure, transistor Q1 is on but not saturated and transistor Q2 is off. This is true because of a careful choice of resistor values and voltage levels. Thus, Vout2 is pulled to 5 volt high through R2 and it can be shown that voltage drop across R1 is about 0.8 volt, so that Vout1 is about 4.2 volt, that is low. When Vin is low as shown in the figure, transistor Q2 is on but not saturated and transistor Q1 is off. Thus, Vout1 is pulled to 5 volt through R1 and it can be shown that Vout2 is about 4.2 volt. The outputs of this inverter are called differential outputs because they are always complementary, and it is possible to determine the output state by looking at the difference between the output voltages Vout1 minus Vout2 rather than their absolute values. That is, the output is 1 if Vout1 minus Vout2 is greater than 0, and it is 0 if Vout1 minus Vout2 is less than 0. It is possible to build input circuits with 2 wires per logic input that define the logical signal value in this way. These are called as differential inputs. Emitter coupled logic NOR gate. To perform the logic with the basic circuit shown in the figure, we simply place additional transistor in parallel with Q1, similar to the approach in TTL NOR gate. If any input is high, the corresponding input transistor is active and Vout1 will be low, that is NOR output. At the same time, Q3 is off and Vout2 is high, that is OR output. We consider the input levels for inverter or buffer as 3.6 and 4.4 volt, while the output levels that produce are 4.2 and 5 volt. This is obviously a problem. We could put a diode in series with each output to lower it by 0.6 volt to match the input levels. But that still leaves another problem. The outputs have poor fan out. A high output must supply base current to the inputs that it drives, and this current creates an additional voltage drop across R1 or R2. It reduces the output voltage. These problems are solved in the commercial ECL families such as 10K families that we can discuss next. The package components in the today's most popular ECL family have 5-digit part numbers of the form 10xxx. This family is called ECL 10K. This family has several improvements over the basic ECL circuit, as it has emitter follower output stage that shifts the output levels to match the input levels. An internal bias network provides VBB without the need for a separate external power supply. ECL NAND gate. Figure shows the internal schematic of ECL logic gate. Generally, it is divided into 3 sections called as input section, differential amplifier section and the output section. As shown in the figure, emitters of transistor Q1, which is PNP, and Q2, which is PNP, are connected together, and the sum of the currents I1 and I2 forms the collector current of transistor Q3, which is PNP. That is, I3 is equal to I1 plus I2. The emitters of Q3 and Q2 are connected to constant current source I constant, that is I3 plus I4. The base of transistor Q3 and Q4 are connected to fixed reference voltage V reference. Consider logic 0 as more negative voltage and logic 1 as less negative voltage, which is nearly equal to 0 volt. The conditions for inputs A and B are tabulated as shown. Consider A equal to logic 0 and B equal to logic 0. Both transistors Q1 and Q3 are on, thus carrying more current. One can observe that I4 is constant and I3 is equal to I1 plus I2. Thus, in order to make I constant as a constant current, I3 has to be adjusted so that Q3 would be more conducting or less conducting. This in turn makes Q2 more or less conducting, and hence accordingly output would be more negative or less negative. This is true for all the cases of A and B. The symbol for 2-input ECL NAND gate is shown. Classification of ECL family. ECL family is classified based on the supply voltages at which they operate. They are classified as positive ECL, also called as PECL, and negative ECL, which is also called as NECL. Positive ECL. These are the devices operating at plus 5 volt and ground. When used in PECL mode, ECL devices must have their input or output DC parameters adjusted for proper operation. PECL DC parameters can be computed by adding ECL levels to the new VCC. Negative ECL or NECL. These are the devices operating at minus 5 volt and ground. When used in NECL mode, ECL devices must have their input or output DC parameters adjusted for proper operation. N ECL DC parameters can be computed by adding ECL levels to the new VCC. We will also note that the voltage changes in ECL are small, largely governed by VBE of various conducting transistors. In fact, the magnitude of the currents flowing through various conducting transistors is of greater relevance to the operation of ECL circuits. They are also referred as current mode logic or CML. ECL subfamilies. Different subfamilies of ECL include MECL1, MECL2, MECL3 and MECL10K. Also MECL10H and MECL10E. MECL1 was the first monolithic emitter coupled logic family introduced by Semiconductor, that is Motorola SPS, in 1962. It was subsequently followed up by MECL2 in 1966. Both these logic families have become absolute and have been replaced by MECL3, also called as MC1600 series, introduced in 1968. Although chronologically MECL3 was introduced before MECL10K and MECL10H families, it features higher speed than both of its successors. With a propagation delay of the order of 1 nanosecond and flip-flop toggle frequency of 500 MHz, MECL3 is used in high-performance, high-speed systems. Comparison of ECL subfamilies. ECL subfamilies, that is MECL3, MECL10K and MECL10H, are compared on the basis of the supply voltage range, propagation delay expressed in nanoseconds, worst case noise margin, speed power product and maximum flip-flop toggle frequency. Characteristics of ECL family. There are many features possessed by MECL family devices other than their high speed characteristics that make them attractive for many high performance applications. The major characteristics are as follows. ECL family devices produce the true and complementary output of the intended function simultaneously at the outputs without the use of any external inverters. This in turn reduces package count, reduces power requirements and also minimizes problems arising out of the time delays that would be caused by external inverters. The ECL gate structure inherently has high input impedance and low output impedance, which is very conducive to achieving large fan out and drive capability. ECL devices with open emitter outputs allow them to have transmission line drive capability. The outputs match any line impedance. Also, the absence of any pull down resistors saves power. ECL devices produce a near constant current drain on the power supply, which simplifies power supply design. On account of the differential amplifier design, ECL devices offer a wide performance flexibility, which allows ECL circuits to be used both as a linear and as digital circuits. Termination of unused inputs is easy. Resistors of approximately 5 kilo ohm allow unused inputs to remain unconnected. High fan out or wired OR connection is the characteristic feature of ECL family as shown in the figure. Let us summarize this module on CMOS and ECL. Let us first summarize CMOS. In this, we have first seen what is MOS technology, what is PMOS and what is NMOS, how these PMOS and NMOS are combined to form CMOS, We have also seen the working of CMOS inverter. We have also compared the CMOS logic families based on the figure of merit, how the propagation delay and the power dissipation are compared based on this figure of merit. We considered this particular CMOS logic family in different output configurations like open drain and tri-state. CMOS logic families are identified in the 4000 series or 74C series. This particular logic family can be interfaced to TTL and ECL. What are the different ICs which are dedicated for this purpose are also considered here. After considering CMOS and summarizing its different parameters, let us see about the ECL. In ECL, we know that it is a non-saturating bipolar logic family. So, in this particular module, we have considered the basic concept related to non-saturating bipolar logic. Then, we have seen different subfamilies of ECL, how this particular subfamily is interfaced to CMOS and TTL using level converters. How it is fast than other logic families is also considered, and the logic levels of TTL and ECL are compared in detail. Thus, in this particular module, we have seen CMOS and ECL. Although their logic levels are different, they are popular depending upon the applications in which they are used.